The warning in this one is very important. We need to check for endpoint convergence. So what I mean by that is when we get our interval of convergence, the ratio test won't tell us what's happening at the endpoints, because that's going to be the situation where an plus 1 over an absolute value converges to 1 at the endpoints. And so we have to individually check both endpoints of our interval of convergence. And it wasn't relevant until now because we either had a degenerate interval, remember x equals 0, or we had an infinite interval, and you can't check an endpoint that's infinity or negative infinity. So this is the first time where it's relevant, but very important warning right there. So keep that in mind. Once we get our interval, then we'll check the endpoints. Okay, so we have the sum n equals 1 to infinity x to the n over n. Start out the same way. We're going to use the ratio test. Absolute value, an plus 1 over an. Okay, you guys help me out here. What's an plus 1? X to the n plus 1 over n plus 1, and then dividing by an, what will that look like if we flip and multiply? There we go. Okay, let's simplify. I will write, okay, would it bother you if I wrote the n over n plus 1 out front without absolute values around it? And then something inside these absolute value bars? The operation is multiplication. Absolute value splits up over multiplication and division. In fact, there's both operations there. And so I essentially pulled out an n absolute value of n over n plus 1, but that's always positive, so I dropped the absolute values around that factor. What's left inside? X to the n plus 1 over x to the n, but you can simplify that. What does that equal? X to the absolute value of x to the first power. Do you buy that? Okay. If you take the limit with respect to n, it's always with respect to n. Take the limit with respect to n and think of x as a constant for now. What does this converge to? Converges to the ratio of the lead coefficients because it's a rational function. Times x, absolute value of x. So 1 times absolute value of x, or just absolute value of x. Okay, but now it's time to think of x as a variable. It could be a real number, right? But which real numbers can it be is the question. Well, we're applying the ratio test. So this limit has to be what? For the ratio, to get convergence, that is. Has to be less than 1. So we need, by ratio test, let me put it here. By ratio test, to get convergence, we need the absolute value of x to be less than what? We need this. That gives us our interval. Do you remember how to solve an absolute value inequality? To get rid of the absolute values, you put the thing in the formula, when it's less than, you put the thing in the formula here, in between the opposite of this positive number on the right side and that number. So these guys, this is what we need. And to write it in terms of an interval using inequalities, that's what it means when you say the absolute value of x is less than 1. It means x is between -1 and 1. Right? But that translates directly to the interval -1 to 1. Does that make sense to you? So the ratio test gives us that interval, and it kind of makes you believe what I said earlier. Oh, okay, so the domain is the set of all x values that make the series converge. And the theorem that I just stated and didn't prove, it's approved in Appendix F in your book, is that the domain is going to be an interval. Now, it could be an infinite interval or a degenerate interval, as you saw in the first two examples, but it can also just be an interval with finite endpoints. So we're saying all numbers in between -1 and 1, you can plug in, create a series out of any one of those x values, and it will converge to something. Now, the thing is, we don't know what happens at the endpoints because the ratio test is going to fail there at the endpoints. So we need to check them. That's what the warning was all about. Now, we could get the radius right now because the radius won't change whether or not it converges, the series converges at -1 or 1. So what's the radius? It's half the length of this interval. You could just take 1 minus a -1 is 2, divide by 2, you get 1. So if you ever, obviously in this one you could do it in your head, but if you ever have endpoints that are weird numbers, you can just subtract, find the length of the interval, divide by 2, that gives you the radius. Just like taking on a circle, taking the diameter and dividing by 2 gives you the radius. But we're not done. If this were a commercial, I would say, but wait, there's more. So this is what the warning was about. Check endpoint convergence. Check for, because you won't necessarily get it. Check for endpoint convergence. So all you do is you say, let's let x be the left-hand endpoint, -1. If x is -1, then, okay, everybody look at the original series. Everybody look up. This is your original series, but if you plug in x equals -1, what does the original series become? If you plug in x equals -1, what does that series become? Sum n equals 1 to infinity of -1 to the n over n. It becomes the alternating harmonic series. How could you prove that that does converge? You already know how to do it. What test do you use? AST. I'm not going to take the time to do it here, but you should be able to do it. I'm just going to mention it converges by AST. On the test, you should be able to show that, right? I can knock out 2 kinds of problems in one with this one example, or with this one kind of problem. So you should be able to show the details of that. Bn is 1 over n, which the limit of that is 0, and it decreases, right? And then it converges by AST. Then what's the other endpoint we need to check? X equals 1. Okay, ask yourself, what does the series become when x equals 1? Just becomes what's called the harmonic. The first one was the alternating harmonic series, and the sum of 1 over n is just called the harmonic series, but it's also known as a p series. Yeah. And what does this p series do? Diverges, and it's so quick, I'll put in the explanation on this one. What does p equal? That exponent of 1, right? Not the numerator, but the exponent, which is less than or equal to 1, so by the p-series test, this thing diverges. Okay, so what does the interval of convergence become? If you include the fact that the original series converges at -1. In other words, you need to include -1. So this isn't quite it. This is almost it. What do you do with this left-hand parenthesis? Good. So we're going to say I is equal to -1 included to +1 not included. And then R doesn't change. One point doesn't change whether or not the length of an interval, that is, if it's at the endpoint. So R is still equal to 1. So this is what we were after. Okay, take a look at that. Do you buy that? Yeah, at this point, we've been in class for a couple hours now. You'll buy anything, right? Anything I'm selling. I've got some oceanfront property in Arizona. You want to buy that? No?
We know what we need to check for the endpoint convergence.
If you get an interval with finite endpoints, you got to check.
Okay.
This was the first example of that.
Okay, got it.
Because the ratio test is going to fail at the endpoint. In other words, it'll be in that condition where the limit of absolute value of an plus 1 over an is 1. So the ratio test tells you nothing.